Can you hear me? I mean, I can hear me, but
Make it. It's nice.
because I don't have the microphone activated.
The
One,
name is
one,
amazing.
two, three.
Advanced Knowledge
Okay.
Institute on Traditions. Amazing. So we'll show when you will have only 5 minutes left. Okay.
So, well, thank you all, Gary, Olivier, David, all the organizers for inviting me to, no? For inviting me to speak in your conference. And so I, first of all, I want to, thank Michelle yesterday for the talk in honor of Chris Maya. That he was my supervisor, my former supervisor. So, and in that sense, I want to honor him also and dedicate this most of this talk to the work we have done with in collaboration with him and her last PhD student was Lidise, that is now in the University College London. And well, I wanted to share with you, and then you will see here part of his work in quantum trajectories. And well, first of all, let me introduce you the quantum trajectory method. It's a method, a wave function free method, and it's based in a hydrodynamical formulation of quantum mechanics, or Bohmian mechanics, as you, some of you know, and it's based on, where's the pointer here? This one. Thank you. It's based on the on the ansatz of expressing the wave function and in the polar form with the fields. I mean the S. And you have the action here, and this exponential is could be the square root of the density distribution. And then you will end up with hydrodynamical equations of motion, the continuity equation for the density distribution, and Hamilton-Jacobi like equation for the action. And in this case, you will have all the quantum effects together in this quantum potential here that depends on the density distribution. And then this is an appealing method in the sense that you can right away switch off or switch on the quantum potentials when you are in some systems where you have a quantum part and classical, I mean, after some, for example, collisions or ionization, like we will see an example that you have a part of at some point of the grid, you have that the particle is behaving already like a classical particle. And there are some many examples where you wanted to treat quantum mechanically a part of the system and classically another part of the system. And this is a method that is appealing in the sense that you can switch on and switch off the quantum effects with managing the quantum potential, not manipulating the quantum potential. And so I wanted to compare it with the usual quasi-classical trajectory method. That's it's nothing else that nothing more that putting the quantum potential to zero. It's a particular case of this hydrodynamical formulation. And also you can also see the Gaussian wave packet method, like also as a particular case where you have the average, the quantum potential is an average over the Gaussian. No? So I will talk mostly about the interactive trajectory representation. This is a method of the quantum trajectory method we implemented, and some test systems. We benchmark this method with the usual systems, the standard systems to benchmark the 0-point energy, the tunnel effect, and all the standard quantum effects. And then we did some, I will tell you about is the laser driving ionization in 1D of the hydrogen atom, 1D model. And then we also, for the 2D model, we studied the bidirectional polarization of argon bromine 2, and I will show you too this example. And at the end of this part, I will talk about also a little bit about the model of matrix isolation spectroscopy, and is it compared with an experiment done by Claudine Crépin here in the next building. And then I will talk also a little bit about another work of non-adiabatic dynamics with a group of Sebastián Fernández Albertin and Quilmes, Argentina. That is the possible link for the machine learning and quantum computing at the end also. No? So, well, let me start by introducing you the quantum trajectory, the interacting trajectory representation. Well, we start with the ansatz for the density. This is a parameterization of the density. It means that we will discretize the density and distribution, the initial density distribution, and we will, with this discretization, we will get this quantum force calculated with the quantum potential. That is, you get an analytical quantum potential. So you have a quantum force that you have to plug in the classic like Newton equations that you have now for your quantum system. That it depends only of 4 nearest neighbors in this case, and then it should, and that's these nearest neighbors are the nearest neighbors quantum trajectories, of course. No? For each trajectory, you have 4 nearest neighbors, and then what you are doing here with the hydrodynamical formulation is that you are mapping the dynamics of one quantum particle in 1 dimension in and classical like interacting classical particles. No? And this is of course this is purely quantum, but you are doing, I mean, you are solving at the end a higher dimensional classical system, classical like system, but the formulation is, I mean, it's purely quantum, of course. And well, of course, there is a problem because these trajectories have to abide the non-crossing rule. So it means that they could be very stiff, the equations of motion when they are very close to each other. So you need to you need to perform different strategies to increase the number of trajectories, for example, to converge to some observables. And then, for example, if you if you want to go to multidimensional, this also it's appealing in the sense that the computational cost will be, in this case, with this parameterization of the initial density matrix and density distribution, is that you will have these 4 neighbors plus times the number of trajectories, and for example in 3D, and you should have, if you have n nearest neighbor times the number of trajectories in this multidimensional space. No? So in that sense, it's appealing. And so this is the, this is Well, a summary of the benchmark systems that we study with like obtain all the 0-point energies of the harmonic oscillator and also the Morse oscillator for different anharmonicities. And as you see, this is the error compared with a mean value of the energy, for example, and well, also the ground state. We did also the dynamics and the scattering and the scattering effect of field barriers and calculated transmission probability that and benchmarked with weight factor calculations and also the spectra. We calculated the spectra and the conversions of the spectra when increasing the number of trajectories. And you can see that you don't need too much trajectories to convert to too many trajectories to convert to the spectra. So now let me talk to you about the first application we did, and it was a laser driven ionization, and we used the soft core Coulomb potential for modeling the one-dimensional. This is a one-dimensional model of a hydrogen atom, and well, we want to see what we wanted to see here was to study the influence of a strong and very short laser pulse in the dynamics of this electron, this ionization. And then, well, these are the parameters that we use for both pulses. We use one pulse with 1.5 optical cycle and with 2.5 optical cycle. And then 0, This is a very short and intense pulse that we then we wanted to see how is the ionization process in terms of the trajectories. That gives you also a nice idea of what is happening with the ionization process and electrons where they going, etc. So in the right part, you can see here the interacting trajectory. You can see here for different carrier envelope phase. Yeah, well, this is the envelope phases here, and you can see here, for example, different envelope phases. How is the shape of the force. And then you have here, for example, for different angles, for different carrier envelope phase angles, you can see the different processes that the ionization process, for example, took place. For instance, for 0 degrees, you have that almost all electrons goes to the left. We said we will say that left is the negative values of X and right will be the positive values of X. And and you can see, for example, the dynamics, how the electrons for some angles you have to they come again to the and interact with the electrons of the core, and then you have many collisions before ionizing the electrons. So this part is nice because you can see all the dynamics, and then we have here the ionization yield. The ionization yield for the shorter pulse and the larger pulse. For the shorter pulse, well, we see that the system for the ionization yield, and this is asymmetry. The symmetry is the number of electrons that goes to the right minus to the left, probability to the right minus probability to the left, over the probability to the right plus probability to the left. So it's that symmetry. It tells you that, for example, in this case, for zero angle, almost all the electrons goes to the left. Here. And for example, for I don't know, 100, you have that all goes to the right. And this is a symmetry parameter. And then you have the ionization here that, well, what I told you is that it converts very fast. In this case, for the shorter test, for not too many trajectories. And in the case of larger pulse, intense pulse, it converts slowly because in this case, you have more cycles and you have then the electrons go to the core, and you have more of this kind of process that the electron has to go to the core and interact with the electrons of the core and go. And this makes the equations of motions very stiff, and so the convergence is slower in this case. No? So, well, finally, you have here, for example, well, the photoelectron spectra compared with a wave packet benchmark, and well, it will produce well, I will not enter into details, but then you can see the interference patterns in the photoelectron spectrum, and we can explain it with a picture of the dynamics of the trajectories. So next, I will go to the second example with the application with a vibrational periodization of argon-Brahman 2, and well, the idea is that you can photoexcite this complex, and then you will get the dissociation of the van der Waals, the argon atom that is that has a van der Waals interaction with the Brahman 2. And then what we did here was to also make a mapping using these quantum trajectories to an effective Hamiltonian that you have, I told you before, you have a higher dimensional classical-like problem now, and these are the 2 degrees of freedom, and then you will end up with this, well, this Hamiltonian with the quantum potential here, and then, well, you solve the equation of motion for each degrees of freedom. In this case, it's a two-dimensional model, and then these are classical-like motions, equations of motion, but of course you have all the quantum information, the quantum potential. So, and we compared the lifetimes of the argon-Brahman 2 excited in different birational states. We compared with the experiment conducted by Ken Yanda in 2010. And as you see, well, the method or the interactive representation well, provides the agreement is fairly good with compared with the experiments, and this is also compared with the wave packet propagation that you see here, this point here in the wave packet, but this in this case the birational mode of the 19 birational mode of the Brahman 2. In this, when you excite this birational mode, you have I mean, the mechanism change in the dynamics is very sensitive. I mean, the mechanism of the dynamics changes, and instead of instead of 2 quantums, you need 3 quantums to get to the dissociation of the argon. So it's very, very sensitive to dynamics in this case. And potential in the surface and the and then, well, this is this example, and then I will give you the last example with this method is a matrix isolation spectroscopy of sodium and argon and sodium and krypton matrices. The experiment was conducted by Llinersy in 2010 also. And well, this is experimental experimental absorption bands, but you have here, well, several different sites of the sodium. What they did here in the simulated, what you say, you see here the simulated data here is referred to the 3 sites, but we only took the substitutional site of the sodium and place it in the substitutional site there. And as you see here, what they did when they simulated here the dynamics, the pure classical dynamics with an effective temperature to account for the 0-point energy, but they get this with gas phase interaction potentials of the sodium with argon or krypton dimers. And then what they did was to shift, to modify the B state, well, by hand, in order to obtain fit the right spectrum. No? So we thought that probably this is because, of course, this is a purely classical simulation, and of course the quantum effects there will be, I mean, for argon most, that for krypton first, it will be important in that cases. And then what we did was to, well, we of course used another parameterization of the wave function in terms of the distance of the atoms in the matrix, and then well, with the minimization like in Caparnello to find out the coefficients, and with the dynamics and with this parameterized density. The advantage of the parameterized density is that you have already the analytical quantum potential already, so you can integrate the equations of motion, and then we obtained the right shift. This is with I mean, this is classical dynamics with effective temperature. And then we obtained well, a right shift for the spectra in both cases, and well, so we can ensure that this is because of quantum effects in that case. So now I will mention some well, the other work that we have done with Sebastian in Quilmes, Argentina. That's has to do with linearized cyclic paraphenylens. That what we studied here, of course, these systems are of interest because of the optoelectronic properties and as building blocks, for example, for materials, different materials. And then what we studied in this case here was how the gradual linearization of the conjugated backbone conformation, like here, no, you add and add, will shift the absorption spectra, for example, and explain it in terms of the polarization of this, the total dipole moment of this molecule. And this was, I didn't include here well, I didn't include the experiment with a Japanese group, but we compared the attendance of how many minutes? And then, for example, here, this is one of the first, I mean, in the experimental results, they didn't have, for example, the population of the S1 excited state, as you see here for the circular, the CPP, the 7 CPP. And well, when you start to linearize this molecule, you start to get some population of the S1 state, and so on, until it's almost completely populated the S1, and the others will it disappears. No? Then, well, and then you can explain here. This is done with non-adiabatic surface coping dynamics, as you know. And then you will you can explain this with also with the dipole moments that you have at the end of the of each linearization of this of each for each state, no? And well, these tenants agreed with experimental results. And then we wanted to study also in the case of carbon nanorings, the one, and there are two different nanorings, no? This one. One composed with naphthyl units, 9 CN, and the others 9 CPP, no, like the ones we already see. And then you see here that you have in this part what we are interested here in this case, and how many modes, how many normal modes participate in the S2 to S1 transition in this, and for both of them, no? And we see, for example, in the left, these are the number of excited state normal modes that contribute to the non-adiabatic coupling from S2 to S1 transition, and at the moment of the transition, no? And then you see, for example, there are few states in both cases, and also you have the projection of these states in the normal modes along the non-adiabatic coupling vector, and you have here, for example, what are the modes that participate the most in or have a longer projection and this non-adiabatic coupling vector. And you see there are very few. Talk about this at the end of the talk, because we are now we were engaging in a project of that connects with the quantum trajectories with this, but because you see here that they are very high frequency modes. They are very high frequency modes. So what we like to do at the end is to treat these few modes. That this is not only for this system. We have checked many systems, and this is happening for many systems, that you have very few modes that participates in the moment of the of the transition from the S2 to S1. And then we wanted to, what we want to do in the future is to treat these few high frequency, high energy modes quantum mechanically, because the 0-point energy is very important in these cases there. No? So also this is at the end of this part. We also treat carbon nanocages, and also we in this in another experiment that I didn't put here. So, for example, we explained the blue shifting of the absorption spectra and the red shifting of the emission spectra by in these carbon nanocages through the exciton migration. I here, well, I can talk to you more about this later if you ask me. But in this first one is, for example, you have the exciton, and what we are looking here is how in these bridge heads, how is the concentration of the electronic density in each bridge head. 1, 2, 3 depends on the number of units, no, you have per bridge. And then, well, what is important here is that in time and t equals 0, you have the concentration of the electronic density for the first. This is the smallest one, no? The first nanocage, because this nanocage is more rigid than the other two. The other two can accommodate themselves to accommodate the exciton, no? And then that's why this one is well, is greater than the others in t equals 0. And then this graph here is how many benzenes are in the case of the bridges, in the position of the bridges, how many benzene units participate in this where the exciton is localized, no? And then in the case of the bridges, and you see what is important here is also that the relaxation, when you relax the system, all the three of them, the exciton is localized in the bridges in 4, sorry, not in the bridges, in 4 units in the bridges. In 4 units, no matter if they have 4, 5, or 6, no matter the size of the bridges, the exciton always is localized in 4 units. And this one tells you how many bridges, in how many bridges the exciton is localized. And it tells you that at the end, the exciton is always localized in 1 bridge. The idea is that the exciton, when you relax, the exciton is localized in one bridge and in 4 units of this bridge, no matter which the size of the number. Okay, so well, the last here is to tell you about this. Well, this I commented to you already. Okay, now this is the idea of the equation of motion that is also related with freeze, because we will do it with mixed quantum classical Bohmian dynamics to account for these few degrees of freedom that are very it has very high energy. So we will treat it mechanically inside this non-adiabatic non-adiabatic dynamics, surface open dynamics. So well, I will more or less, well, I did maybe give you some, well, I have already set some ideas, and we'll skip the conclusions. And well, with machine learning, of course, with the idea is the evaluation of the quantum potential. Of course, we can train the system to like in surface potential analysis surface. It's the same idea, no, with quantum potential. And in the sense of quantum computing, I want to add that the Hamiltonian of well, I will talk about this. The collective electron oscillator formalism is the one that we use for the describing electronic states on the fly in this non-adiabatic excited state dynamics. And this one is this Hamiltonian is written in second quantization, so it could be appealing to use quantum computing to compute all the observables because it's already written in second quantization form. Okay, thank you all for your attention.
Okay, thank you very much for your talk. Are there any questions in the audience or online? Nadine?
This is horrible.
Thank you very much. It's about the vibration on bromine. I was surprised that you were comparing with experiment rather than with the wave packet, because actually the reference here is the wave packet calculation, right?
This is wave packet calculation here.
Yes, so you're saying, but you said you have a good agreement with experiments, and there is no reason. I mean, maybe it's just by chance. Or one thing that was surprising me physically is that when you have the closure of delta V equals -2, so when you need a third quantum to vibrationally predissociate, for V equals 19, you should see a drop in the vibrational predissociation rate, so a longer lifetime, and you don't see that. So you see it for V equals 20, maybe. So I was wondering if there is, are you using the same potential as the wave packet? Or is there something that would explain the difference?
But it's different in the sense that this is a two-model problem. So it's fixed
it's a two-dimensional problem, you say.
Two-dimensional problem, so it's fixed.
Yes, but in this case, the rotation is not very important.
But in the case of wave packet, for example, we saw, because we wanted to see why they didn't get to very well this part, no, this particular point. And the paper of Octavio, we saw also that the wave packet in that case is very spread initially.
But you should have that too.
Yeah, no, but because it's the problem is that this is initially, but very fast, it localized in the T-shaped form. That is what we have. We have the T-shaped form fixed because we don't have. This is a two-dimensional model with a T-shaped form. So,
but the T-shape is not the most favorable configuration for dissociation.
In this case, because there are two time scales in the experiment. One is for the linear configuration, and the other one is for the T-shaped configuration. And the one for the linear configuration goes, in the experiment goes to very fast, and then
that's a completely different story. I'm sorry. The linear and the perpendicular are two isomers, and that's a different. Okay, so it's a different process. One is just direct dissociation, and the other one is vibrational predissociation.
Yeah, but I mean, what you
discuss it later.
No,
yes,
what
sorry.
I mean is the time scale. That the time scale of a linear isomer, it gets very fast, and then what you measure in the experiment is the T-shaped form mostly. So this is what I meant with that.
Any other question on that talk? Unless the fact that we should trust more a wave packet calculation than experiment. This I don't get the point, but you can discuss.
One potential, when you use one potential, your reference.
Yes, I agree. Okay, if you want to compare the method, okay, I see your point. And okay. No, okay. Now I understand what was your argument.
The wave packet doesn't work very well in this case, no, compared with the experiment, because well, we can discuss it later, but we also ask ourselves the question why it didn't work. But this approach is, I mean, this is quantum mechanics, and this is not an approximation. This is, I mean, what we are doing is quantum mechanics also. It's not classical. So it's,
yeah, as well.
yeah, I know, but I mean,
so let's discuss that over lunch, because there is the constraint of going to lunch as well. We already took some kind of liberty with the schedule, which I think is nice. But now we should go. Thanks again thanks for all the speakers, for this morning session. And let's come back here at 2 o'clock, right?